Okay, here we go. Planetary motion. I want to do it at least two different ways. Most people do it the Newtonian way, which is really, really hard, and I'll show you how easy it is to do it the Lagrange way. So when things move, you have to do equations of motion. Agreed? Anytime you have a thing moving, you have to do equations of motion. So when planets move, you also have to do equations of motion. So let's do that one. That's like the first law. What was the first law again? Can someone remind me? What was it called?
It's the law of ellipses.
The law of ellipses. So we are going to now find the equation of the planetary motion as a planet moves around the sun. Okay, so that is the first law. We said we were going to do opposite today. It was opposite day today. We started from the third law, we went to the second law, and now we're back to the first law. And that law is called the law of ellipses. And we are going to find out the equations of motion for planets.
Yay.
It's very cool. Okay, so let's first do this the Newton's way. And I'll show you how torturous that is. We won't do it, I promise, but it's done in the book and you can look at it. So imagine you have a planet that moves around a star. Of course, it's not going to be a circle. So I'm going to change this and I'm going to make it into an ellipse. I'm going to make it into an easy ellipse. Okay. Then I'm going to say that this planet sweeps out this area. I'm going to call this S, R, and phi. Not surprising, right?
No.
Okay, good. So in Newton's laws, we are still going to use polar coordinates, R and phi, because it's a two-dimensional problem. So in Newton's way, how many equations will we have? Good. Which ones? One along the R and one along the phi. What's the force that's acting in the R direction that's keeping it together? Good. Which one? Small one or big G? The big G one, right? Okay. And what's the force what's an external force that's keeping it moving in phi direction? There is none. So this means I can rewrite this as MAR equal FG as a function of R. And this one I can write MAC equals 0. This equation is called the radial equation. And this one is called the transverse equation, also called the circumferential equation. Now there comes the hard part. We know that x equals r cosine theta and y equals r sine theta. We have to find these values. Right, so we can plug them in. That is actually exceptionally difficult. And let me show you how difficult it is, because I did that at one point in my life. So it is done in chapter 1. If you want to go look at it, anybody, you should do this for yourselves. At one point, sit down and actually derive them. They are here, and they are very, very long and detailed. Okay, and then in Cartesian coordinate. Then you have to go to Appendix B, because I don't know why I did them. But if you want to do velocity and acceleration in polar coordinates, you have to do r hat, phi hat, come up with theta and phi's in both of these coordinates, differentiate them to give you something like this. And from there, you can derive an expression for v. And from there, you can take the derivative with respect to time and come up with this expression right here. It is long and it's tedious. I have done it. So if anybody's interested, you can come in and look at it. For now, takes like a couple of pages of math to do this. I mean, not a couple, maybe half a page. But anyway, I'm not going to do that here, but just know that it's quite tedious.
Okay.
If you trust me, I'm going to put the value down here.
Go.
Acceleration in polar coordinates as a function of r and phi will now be given as r double dot minus r phi dot squared r hat plus r phi double dot plus 2r dot phi dot phi hat. So in order to come up with these equations, we have to take this part and plug it in for the radial equation and this part and plug it in for the transverse equation. So the two equations above will then become mr double dot minus r phi dot squared equals f of g, which was minus gmm over r squared. And this one will become r phi double dot plus 2r dot phi dot equals 0. This is called, again, radial, and this is called transverse equation. Okay, I also want to show you something really cool. We can develop the second law from just this expression. You want to see how? If you take this one, this is fun actually. If you take this expression, what does that mean? M cannot be 0 implies r double dot plus 2r dot phi dot must be 0. I'm going to tell you that if you open this expression, you will get that. So we're working backwards, which means r squared phi dot is a constant. Right here above, did we say r squared phi dot was L over M?
Mm-hmm.
Okay, may I plug that value here? R squared phi, what will I get? L over M is a constant, which means L is a constant because M, of course, is not changing. Which law was this one? So the first law proves the second law. Woo-hoo.